We're talking about John Walk's paper earlier. He did one at 2 o'clock on basically a lot of permanent attachments that, and a project he's working on to qualify those for the Navy. My paper should have preceded his probably because I'm looking more at the basics of adhesives and some of the potential for use of adhesives in the shipbuilding process. In the shipbuilding process, a lot of times what we'll see are temporary welded and now this one's a combination of welded and bolted. Great. So the pointer here doesn't work. Or does it? Does this work? Yeah, there it is. So anyway, these are stud welded, and then they have bolts to try to hold the plate intact. The problem is, anytime you do any temporary welds, you have to break those welds off. Often when you break those welds off, you damage the underlying plate. So you're into the cost of welding these attachments and then also making the repairs after they're done. So that's sort of my aim is in how to avoid that. A couple other things you like to avoid are, if you're using adhesives, you're not doing hot work. You don't have to gas free. You can effect temporary repairs, sometimes fairly quickly at sea. And you can avoid galvanic corrosion because it's somewhat insulated, or at least galvanically insulated. Sort of the thing that came to mind when I was thinking of the hot work thing was the French liner Normandy. In the late 30s, the French decided, the owners decided to park the Normandy in New York because things were getting a little hot in Europe. When the U.S. got into World War II, they took over the Normandy, decided to make her into a troop ship. They were doing some welding in the after part of the ship to make some modifications. A life jacket locker caught fire. Basically, the ship started to burn fiercely. The New York Fire Department poured water on it until it capsized. And that's what you see in the lower right. Sat there for a while. They figured they couldn't salvage it. They basically just scrapped it from hot work. Of course, I don't know what adhesives. I doubt they had the adhesives then that we have now. But hot work can be a bad thing. You can avoid that somewhat with adhesives. So a little background information. Adhesives come in a bunch of different forms. This is a fairly simplistic look at a range of adhesives from epoxies through methacrylates and on to basically simple polyurethanes. And on the vertical axis, we got their lap shear strength. We just take adhesives, or you're doing a test, you put two parts together and you lap them and you pull them apart. And that's the best way to load adhesives. We'll see that later. The other axis is elongation. You can get a lot of stretch out of some adhesives, but sometimes too much stretch, not enough stiffness is a bad thing. So you got to look at the application and balance the strength with the toughness. We just talked about the the lap shear thing. That's the best way to load adhesives, and that's a sort of a diagram that shows that test. Pure tension, pure compression, and sort of the weakness of adhesives is in peel. But the shot towards the end, we'll see where that can actually be an advantage to us. Failure in adhesives, you either fail the joint in the adhesive, which is called a cohesive failure, between the adhesive and the substrate that you're trying to bond together, called an adhesion failure, or if you have a really strong adhesive and a weak substrate, such as, say, an epoxy and cheap E-glass laminate, it's quite likely you're going to fail the substrate or the underlying material. In steel, shipbuilding, which is most commonly the form amongst most of these SNAMI get-togethers, we're not usually failing the substrate with adhesives. But I know some of you out there, you know I've got more of a composites background, so it's sort of a toss-up as to what your adhesive is and what your materials are as what's going to fail when you start to pull things apart. Sort of an interesting read on the adhesives when I was doing some searching around, and click bond was measured. I think they're one of the partners in the in John Walk's project that he's working on at Ingalls, and they're funded for. And this is a series of shots I stole from ClickBond's website, but I thought it was very interesting. It's nicely explained. They do a nice set of short videos, So I stole those, and I was allowed to do that. I got permission. But basically all they're showing here is they've got a very simple, they're not applying a lot of adhesive, so they don't need a whole lot, at least in certain small applications. So they got a 2, you can see this cartridge here, that's the adhesive. That's about a 2-to-1 ratio adhesive. You pump those into this little mix head you screw on, it swirls the adhesive out the end, comes your adhesive. If you're into bigger applications, which is in some situations we would be looking at, you can use something like an air-powered caulking gun and get a bigger tube, like a big tube of caulking or adhesive you'd use at home, but a little fancier adhesive for what we'd be using. You get into bigger applications, you can pump it out of a drum. This is a picture of a big machine that pumps it out of a 55-gallon drum. If you're into big applications, the adhesive that comes in a drum is going to be a lot less expensive than little bits of adhesive that come in these little cartridges. You got to do a lot of pumping to pump a lot of adhesive out of one of those. So again, depends on the application and what you're using. So in the nice ClickBond series of videos, they'll show you putting just the right amount of adhesive on their little attachment there. And they can, the ClickBond, I think their patented method is this little plastic enclosure that when you apply that part, you push the center of it down, what pushes the, basically see the stud right there. See the adhesive starting to spread out below that. The nice thing about it, it gives the right amount of pressure. So they have this QC system built into their patented application. And when the center of that plastic part clicks, then you leave it there. Actually, on this particular application, they have peel and stick tape right there, so it holds it in place. So it holds that item in place until the adhesive cures. Sort of a nice series of events. It's not quite totally foolproof, but it's pretty interesting. So then when you're all done, you have this nice fillet, nice even adhesive all around it if you put just the right amount on there. The reason I put the question mark on the finish there is part of this is the surface prep. You can see where what looks like a primer, a weldable primer, has been sanded and ground away so that you have a clean surface to bond to. So you get a better bond. You get a better bond to a sanded steel surface than you do to paint. If you're using a lower loading requirement, you could just stick it to the paint. Then the strength of the adhesive is most likely the strength of the paint. That might be all you need. Here you still have to repaint. Didn't want to give ClickBond all the credit. There are some other companies out there that have this. We're supposed to be non-commercial, so I try to make everybody happy. A couple of other companies are Weld Mount, and they've got, you go on the web, get a bunch of pictures of the things they do. And another company, Rotolock, or that seem to be the other two competitors to ClickBond. They have some slightly different arrangements and styles of gizmos to attach, but all of these are set up to be bonded to other parts of steel ships or aluminum ships and somewhat eliminate the need for either stud welding or other welding, which, like we looked at, involves hot work or gas freeing and usually paint touch-up. Wanted to take a little sidetrack here. We talk about adhesives and we think glue's pretty weak stuff. But the Swedes didn't think so. They built a 72-meter Corvette. And if it's all composite, it's basically all glued together. That's just a bunch of glue and fabric stuck together. Stick a couple of gas turbines and a gun on it. It goes 40 knots, and they've been doing a really good job. There's a whole other story behind those. It's not as simple as it sounds, but they did a nice job on these boats. Another interesting little adhesive demo is this. I think these guys, Shat Harding, have the world record for free fall lifeboats. I think this would make a great amusement park attraction. Hop in here, take a ride. I always wondered what happened to the guys in the little boat down here. Looks like they're going to get. They didn't get swamped. If you get to the right website, you see the video of this. It goes through the water pretty good. But that whole structure is bonded together. There's no taping, there's no welding, no studs. They just had a bunch of plates. They molded the hull and all the framing and this is one of the transverse framing members. They just have big fillets glued in there. They didn't even have taping joints. They just glued it together. Of course, they let the glue cure first, and then they tossed it off the ramp, and that was pretty good. So if we go through our range, and the adhesive used on that was not the super high strength stuff. You'd think, my gosh, with those kind of loads, you use the high strength stuff. For them, the most efficient one was sort of a medium strength, high elongation, tough urethane acrylate, the kind you could pump out of a drum. So if you're building a series of boats, you could pump your adhesive out of a drum, make those nice fillets. And I've actually designed a few boats that are designed to be put together just to be glued together. So a lot of the historically known way of sticking fiberglass boats together is to put a bunch of fiberglass tapes in everywhere. And that can be a little bit time consuming, not always necessary. So if we get back to our shipbuilding problem is we have all these temporary attachments. If we're trying to pull chunks of a ship, in this case a part of a deck house, I think, together, we have all these temporary lugs that are welded on. If you've ever been involved in this, when you're all done welding up this nice butt joint here, then you have to break all those lugs off. Frequently you break them off, you destroy some of the underlying plate. So then you're into weld repairs of the plate. A lot of effort into putting them on and taking them off and doing repairs. So the idea is if we glue it on and we load it properly, if you noticed, remember we talked about peel being a bad thing. So if we glue something like a pad eye on, if we're going to take a strain on a chunk of the ship to pull another chunk of the ship into it, if we load the pad eye such that it's loaded in shear, then we get more strength out of an adhesively bonded pad eye than we can out of a welded pad eye. If you take a high strength epoxy, take a safety factor of 4, you can pull about 180 tons with a pad eye that's glued on, still with a safety factor of 4. If I put a 1/4 inch fillet weld all around the perimeter of that and use the same safety factor of 4, I can get about 45 tons. So I can get more strength out of a glue joint than I can out of a welded joint. Of course, I could use bigger welds, but maybe I could use more glue too. But when I go to pull that off, I can start at the corner and pull the thing off. And actually a weakness of adhesives that John addressed is some of the environmental conditions. You have real high temperature, say in a fire or in a high temperature space, like a boiler room or something, you may exceed the high heat deflection temperature of the adhesive and you'd lose strength in it. But that can be used as an advantage as a temporary attachment in shipbuilding and just heat it up and peel it off. So that's it in a nutshell. We get half an hour for these things. I don't want to expand too much, but basically just a short run through on adhesives, strength of adhesives, and a methodology for using it in the shipbuilding atmosphere. Any questions? Eric, of course you have questions.
Yeah, John talked a little bit about, some questions came up about working temperatures. And specifically, he said in his presentation, well, these are only going to be approved for sprinkled spaces where the temperature is not, he was like throwing out a number like 250 F. Now, does that sound like an upper limit for adhesives?
I would say, yeah, for common adhesives, commonly available adhesives, there are, as usual, higher temperature adhesives and resin systems that can be made. But in what I find in composites and adhesives like that, the higher temperature you go, the more brittle the material becomes. So you can get a higher strength and a higher TG, which is a glass transition temperature, but then you lose some of your toughness. And you have to look at that as part of your design criteria. Can you lose that? Do you need the toughness? Is it just a static load? If it's a temporary shipbuilding type thing, it likely could be a static load. If it's a dynamic load, you want to have some toughness in there so it has a little give. So it's they're developing. I see higher and higher temperature applications all the time.
Yeah.
So I don't think he'll have.
Bond product that was the Navy had already looked at. I think they're going to look at Plexus as well. And he also said that the test program they were doing was a very cold temperature too for brittleness, which I was surprised to hear that the Navy went
Well, actually, that's...
They're inside applications and not out exterior.
Yeah, that's one of the bugaboos about composites with the Navy. Years ago, they put some pultruded stanchions. I don't know if you remember seeing that. They put some pultruded stanchions on a destroyer, basically the test destroyer. And they were operating in the Arctic, and it was really rough seas, and some guys were out on deck, and they fell against the stanchions. And because of the cold temperature, sort of like a Titanic type of thing, the stanchions snapped, the guys fell over the side, and they lost them. So you can understand the Navy then gets very particular about testing new things. So that's why you see low temperature and high temperature applications, and limited applications. But it's sort of like the switch from, wood ships to steel ships, riveted steel ships to welded steel ships. There are fits and starts in the processes. And we've had the same in the composites industry. Anybody can screw up a composite boat too. We've seen plenty of it. And in the adhesives, I've seen plenty of applications, poor surface prep, poor mixing. There are a lot of ways to mess it up. So the Navy's being, in its due diligence, very careful about these applications. John talked about the putting wireways or wire ties on. Every third one has to be still a welded one. Okay, so two can fail, but the third one will still hold it up. If you have a fire or a real high temp, you have a fire in the next space and you melt the adhesive off the bulkhead. So they're working on those applications, looking like they're coming up with some good standards. Any other questions? Yes, sir.
In a scenario where you might use an adhesive instead of a welded-on cat eye for a lifting application, it would have to be load tested.
Yes.
Do you envision you use the same kind of load test, or do you have to do something longer duration to account for potential creep or something like that?
Well, that's a good question. I think what I usually find as a criteria for creep, if you load something like adhesive or viscoelastic material to about 80% of its breaking strength, then you got to worry about creep. But I thought I was being reasonably conservative here and using a safety factor of 4. So I'm only loading it to 25% of its ultimate strength. I wouldn't worry about creep in that application. We're not even getting close to it.
You could probably test it then the same way that you would test any other cat eye, short duration test.
Yeah. And if you got a pad eye holding a load for at 25%, we're worried about creep at that very low stress, I would say you need to speed up your shipbuilding operation a little bit. It's hung there too long. Anything else?
I thought something else. The clip-on thing that you showed, that little plastic thing, obviously that kind of controls the bond line thickness.
Yeah, that's the other nice thing about it.
Right. Yeah, and then I'm comparing it to the large-scale application what you just had up there of the big pad eye.
The big pad eye, yeah.
And larger things that aren't, small uniform pieces like this.
Mm-hmm.
Have you seen a good way of practice to control the bond line thickness and to ensure you have 100% coverage on the surface as well?
I've seen it, say, in the lab or with people that really know what they're doing, but usually what I see in the field is overuse of adhesives, where they put on way too much. And sometimes adhesives, it's bad. You get them too thick, like a methacrylate, like a plexus or a weld-on methacrylate. You get them too thick, they'll boil. They get hot. Or some adhesives will actually crack. You get them too thick, they'll self-crack themselves from the exotherm and in the process of curing. So it's good to get the thickness right. And it's it's interesting on the click-bond thing that they've got this little, you put the right amount of pressure, it squeezes it down. It seems pretty good, but then you look at, in actual practice, you could have a temperature swing of, say, if you're in a shipbuilding atmosphere, it could be, say, somewhere around 45 degrees to 95 degrees. That same adhesive is going to have a much different viscosity in those different temperatures. So it's going to squeeze out differently. So in this application, it's somewhat, it squeezes it down and it stops at about the right thickness. So it somewhat takes care of that. So even if you had different viscosities, it shouldn't vary too much with that. Now, if you're hand applying it, well, that's going to make a big difference. If you're in a hot atmosphere and you're sticking it on by hand and you don't have this control, You could easily just squeeze most of the adhesive out, and that's just as bad as not having it. You have a too thin adhesive line. So a lot of variation in that, and that's, you know, that's one nice thing about this. It gives you a little quality control to it. All right. That's it on sticky stuff then.